Okay, thanks a lot for inviting me. And as Bernard said, this will be about using the moment sum of squares hierarchy for dynamical systems and control. And so what the setting will be, it's going to be that of ODEs on Rn. So we are on a finite dimensional state space. For now, it's going to be the all of Rn. And we have either an uncontrolled ODE driven by a vector field f. So if you give me an initial condition, this vector field will produce a trajectory which moves along the vector field. We'll also be dealing with the controlled setting where we can influence the vector field. So that's the right-hand side of the ODE by some control. And you can decide to do various things with the vector field. You can, for example, decide to stabilize it to the origin. So that would be the green trajectory here, influenced by that vector field, by that control. And so about the dynamical system, we can ask a number of different questions. One of the most fundamental question, which has been studied since the work of Lyapunov and others, a long time ago, is that of stability. So the question of whether all trajectories converge to the origin. Other problem is that of reachability. So what is the set of all states we can reach in a finite amount of time or in infinite amount of time from a given set of initial conditions. And there are other problems such as optimal control. So we want to minimize some function or subject to constraints on the control and states. Problems of regional attraction, which I'll talk about later, and problems of invariant sets and invariant measures. I will not touch on these. And so, by the way, feel free to stop me and ask questions directly. You can just turn on your mic. I think that's the simplest way if you do not understand anything or you just want to ask a question. So now I would like to draw the analogy between the polynomial optimization and dynamical systems, or how can we go from static polynomial optimization to doing optimization on dynamical systems. And so I believe that most of you are familiar with this setting of static polynomial optimization, where P is a polynomial and you want to find its infimum over some closed set X, where X is now subset of Rn. So at this setting, this doesn't even need to be polynomial. That could be an arbitrary function. And you can easily show that this is equal to the infimum over all non-negative measures supported on that set X, which are normalized to 1. And the proof is very simple. Basically, you can just see that if you have a minimizer on the left-hand side, on the right-hand side, you can just put the Dirac there and you get equality. If you have a minimizing sequence, you put the Diracs on the elements of the minimizing sequence, and again you get equality of the infima. And the right-hand side always will give you an upper bound because you are optimizing over non-negative probability measures. So this is the setting of static polynomial optimization. Now, you might want to decide to try to generalize it in the most straightforward way to dynamical systems. So the first idea would be doing something like this. So you would be given some functional P of the solution to this ODE, which let's say be defined on the interval 0, 1, starting from some initial condition x0. And then you can show again by exactly the same argument that this is equal to the infimum over all measures supported on the set of solution to this ODE on the time interval 0, 1 with that initial condition. So this is that set F, set A indexed by the vector field F and the initial condition x0. And you again normalize to 1. So the proof is exactly the same. We never used the fact that the set X was a subset of Rn. And so the first problem with this that you notice is that now the set A is some subset of a function space. So this is something much more complicated to work with. And the second problem you may notice is that perhaps this problem on the left-hand side is not very interesting because you are fixing the initial condition of the ODE, and so so this would have a unique solution provided that f is Lipschitz continuous, and so you could evaluate the value of this function just by forward integration. So you can generalize this and make it more interesting. You could, for example, ask that that on the left-hand side you want to minimize over all initial conditions belonging to some set x0, which is just a subset of Rn. And on the right-hand side, you would just adjust the set on which the measures are supposed to be supported. So you would want the measure to be supported on the solutions of the ODE on interval 0, 1, and such that the initial conditions belong to this measure x0. So that's the first generalization you can think of. And the second generalization is to add control. So you would want to now optimize over control inputs and over the initial conditions. And again, you could reformulate it in the same way. You would just modify the set on which the measures are supposed to be supported. Now it would be on the set of all solutions to the ODE with the initial conditions in the set x0. So here is a typo. That should be inclusion in the set of x0 and driven by some measurable control input taking values in some set U. So is that clear? If so, then I'll try to tackle the problem of working with measures on infinite dimensional spaces, which is hard. And you may have gotten a taste of it in the talks of Selma Kuhlmann and Maria Infusino, that the theory behind it is hard, and currently computationally there is not much that we can do with it. Even though it's still an open and interesting research direction. And so I'll try to reformulate the problems on the left-hand side that you have just seen as linear problems in the space of measures, but such that the measures are supported on subsets of Rn, on subsets of a Euclidean space. And with those, we can work much better using the moment sum of squares hierarchy that this workshop has been revolving around. And so the key concept there will be that of occupation measures. So I'll introduce them in the simplest possible setting of uncontrolled ODE with the Lipschitz continuous vector field F. And so then if you give me an initial condition, this will define a unique absolutely continuous trajectory. And so to that trajectory, I'll assign the occupation measure denoted by mu, which to every subset of the product of the time and space, it'll assign the amount of time that the trajectory spends in that set. So so it's important to realize that it lives on the product of the time axis and the state space, and otherwise the definition is very straightforward. It just measures the amount of time that the trajectory spends in that set A. The key property of that occupation measure that I have just defined is that you can replace integration along the trajectories of the ODE by integration with respect to the occupation measure mu. So if you give me any function g, which is a function of time and space, and you compose the spatial component with the solution to the ODE, then the integral from 0 to capital T will be equal to the spatial integral along with respect to the occupation measure of the function g. And the way you can see it is using basically a classical Lebesgue integration theory. If you take g to be the indicator function of a set A, then it's just the definition of the occupation measure, and then you can proceed by taking non-negative sums of indicator function. These are simple functions, and using limiting arguments. So this is the crucial property that we'll be using. And we'll be also using two other measures which take care of the boundary conditions. So that's going to be an initial measure, which in this case would be just a Dirac at an initial condition x0, and a final measure, which will be just a Dirac at the map of the initial condition x0 through the solution of the ODE. So these will be the three measures that will be appearing over and over again. And now we would like to derive an equation which links them to the vector field F. So we'd like to decide when does the triplet of these measures, when is the triplet of these measures generated by a vector field F of the ODE. And so for that, I'll take a test function which will be in C1, and it will live on the product of the time axis and the state space. And I'll use calculus. So I'll compose it with the solution of the ODE with my trajectory, and I know that by the fundamental rules of calculus that if I take the integral of the total derivative of the function phi composed with the trajectory, then it's going to be equal to the difference of the endpoints. And then here on the right-hand side, I'll use the chain rule. So I know that this will be the partial phi, partial t plus partial phi, partial x times f, because I'm composing with the trajectory. So x dot is equal to f. And it's all evaluated at t and x of t. And so now, here on the right-hand side, this is nothing but a function, this function composed with the trajectory of the ODE. And so I use that key property that I just introduced and replace it with a spatial integral with respect to the occupation measure. And on the left-hand side, it's even simpler. These are just evaluation of the function phi at the final time and at the final point of the trajectory, and the same for the initial condition. And so these are just the differences of the integrals with respect to the final measure and the initial measure, which are just Diracs at the final condition and at the initial condition. So now equating the left and right-hand sides, I get this equation, which is required to hold for all C1 test functions. So the variables in the equations are the three measures, and phi is just a test function. And so the first observation to make is that this equation is linear in the three measures. So that if you give me two triplets of measures that satisfy this equation, so will their sum and their arbitrary linear combination. So this will be very important when we do optimization. And so now I would I'll just mention that you can rewrite this equation in this weak form where you forget about the test functions, but this weak form has to be interpreted in this way. So whenever you see this, I'm actually talking about this equation. This will be just a shorthand. And now the question I would like to ask is the reverse one. So basically I would like to see what kind of measures can satisfy the equation that I have just derived. Is it only the measures that come from the trajectories of the ODE, or are there some other measures that could satisfy that linear equation? So stated precisely, I'm investigating what does the set of all solutions of this equation look like when I fix the initial measure to be Dirac at a given point in Rn, and I restrict the measures to be non-negative measures. And the fact is that if f is Lipschitz continuous, then this is going to be a singleton given by the trajectory starting from that initial condition. And so this statement is actually relatively easy to prove. So let's try to do that. So I'll assume that I have two solutions indexed by the superscripts 1 and 2, both starting from the same initial condition mu0. And what I'll do is that I just subtract the two linear equations that they satisfy. And this gives me this equation where 0 is here on the right-hand side because the initial condition subtracted. And on the right-hand side, I get just the integral of this expression with respect to the difference of the occupation measures. And on the left-hand side, I get the integral of the difference with respect to the final measures. And so now, what we would like to do is to choose the functions phi such that I can produce here on the right-hand side anything I want, and I want to kill the left-hand side. In that way, I'll conclude that mu1 is equal to mu2. And so, as stated more formally, I want to solve this equation for arbitrary right-hand side, which is C1. And I want to find a C1 solution which satisfies a boundary condition that at time t, it should be equal to 0 on all of Rn. And if I succeed in doing so, I can conclude that the integral of psi with respect to the difference of the two measures is equal to 0 for all of psi, and hence the two measures are equal. And then I know that the whole right-hand side is equal, and therefore the left-hand side must be equal as well, because then I can put whatever phi I want here on the left-hand side, and therefore also the terminal measures have to be equal. So let's try to solve this equation and see whether we can do it or not. As it turns out, the solution is very, very explicit and very intuitive. Basically, you use the properties that here on the left-hand side, what you are looking at is the total derivative of the function phi along the solution of the ODE, and you are prescribing it to be psi. And since the ODE has a unique solution, the vector field is globally Lipschitz, so it's homeomorphic on Rn. So you can just flow it from the given terminal time, and you can determine the value anywhere in 0t and anywhere in Rn. So you take the value at capital T, which is 0, and you flow it backwards with the phi dot is equal to phi, and you get the value here. If you want to write it formally, you get this integral here, where capital X is the flow of the ODE, and this concludes the proof. Modulo a little bit of regularity. If F is only Lipschitz and not C1, then you have to modify to actually get a C1 solution. And so now let's finally do some optimization with this. So what I have just told you is that this set P is a singleton when we take the initial measure equal to Dirac at x0. But I'll try to do something stupid. I'll try to optimize over this set. And the functional I choose to optimize is simply the integral of h with respect to the occupation measure. I could have chosen different functionals, but here for simplicity I choose this one. So let's see what this gives us if we approximate this this infinite dimensional LP using the semi-definite programming. So I would just like to dwell on the point that this is indeed a linear programming problem in the space of measures. So the objective is linear because it's just integral with respect to the occupation measure, and this set P is nothing but an affine section of the product of the cones of non-negative measures supported on certain subsets of Rn, and cutting it with this linear subspace defined by that linear equation that I have just derived, and by this initial condition. So that's an affine condition on mu0. And so now we'll try to do the semi-definite programming relaxations of this infinite dimensional LT. And so we'll try to do it in a systematic way such that we end up with outer approximations to the feasible set. So I just proved that the feasible set is a singleton. So that's the black dot. It's just a single point. But if you do outer approximation, you will get some non-trivial information from the optimization problem. And so how do we construct the outer approximations? So that's where the polynomials and positive Stellensatz come into play. So we'll assume that the objective functional and the vector field are polynomial, And the way we construct the approximation is the following. So we restrict the set of test functions to be only all of monomials up to degree 2k. So we know that polynomials are dense on compact sets. So this is this we can do. We can pick a basis of the subspace of polynomials of degree 2k. For example, monomials, and that's what we force the test functions to be. There'll be only finitely many of them. And we'll also construct semi-definite programming representable outer approximations to the cones of non-negative measures with the respective supports. And so you have seen several talks that talk about that, and several courses. So I'll not go into details on that. You can, depending on what set you work with, you can use various positive Stellensatz or the dual versions on measures. The most popular one is the Putinov one, which is also the one I use in all of the numerical experiments in this talk. But you could, in principle, use any other, provided that your set satisfies these conditions. And so, if you do that, if you construct these outer approximations to this set, the set pk, then you end up with just with an SDP that you can solve using whatever SDP solver you want to. And by construction, you will get bounds on the value of the functional p, which is nothing but the integral from 0 to t of the function h evaluated along the solution of the ODE. So if you do infimum, you get a lower bound. If you do supremum in the optimization, you get upper bound. And provided that the supports are compact of the measures, then you get convergence using Archimedean. If the sets are Archimedean, you get convergence using the standard arguments. And so this might sound quite silly still, because this we could evaluate easily using integration of the ODE, and we would get very, very precise results. So this is something this is something where you would not want to use this hierarchy, but let's see what you get numerically anyway as a proof of concept. So I'll take this Vantable oscillator system. I'll choose an initial condition, and I'll draw a trajectory. I'll compute the value of the function numerically, and I will compare with what I get from this hierarchy. And so I have picked for the objective functional this x1 square minus x2 square integrated from 0 to t. And the bounds that you get when you pick the capital T equals to 1 are as follows. So for the order 2, the bounds are quite loose. For order 3, the bounds basically coincide to 4 significant digits. If you do that on a longer time interval, you have to go deeper into the hierarchy to get more accurate bounds. So this is quite intuitive, and you can also justify this analytically by analyzing convergence rates of these bounds. You can also do other things with the solution to the SDP. So here we just looked at the objective values, but you could also decide to use the information in all of the moments that you have gotten from the SDP. So in the SDPs, you optimize over these truncated moment sequences, which are approximations of the true moments of the occupation and final measures. And so you could try to recover the trajectory from it, or at least convince yourself that indeed they concentrate on the trajectory. And so this is what I did in this numerical experiment, and I basically fitted an atomic measure to the moments, and you can see that indeed it resembles the picture that you saw before. And indeed, whenever the color is more red, then that's where the trajectory moves slower. So that's where the occupation measure puts more mass. You could also try to recover the components one by one. So this is now in time on x-axis, and first spatial component on the y-axis, and here the second spatial component on the y-axis. You can see that this is this does resemble the true result, but it's far from accurate. So you would definitely not use this method to solve an ODE. But we'll see that as we go and try to solve more complex problems, this method will still manage to give you informative results, whereas simple ODE solving will just not work in that setting. So the first generalization that you could think of is to pick arbitrary but still fixed initial measure. So what happens in this case? We are now fixing this initial measure to be some nu, and we know by the same argument that still the set of solution to this linear equation is a singleton. So again, we are not expecting anything too meaningful to happen, but the interpretation is quite nice. Basically, you'll be averaging the occupation measures generated by trajectory starting from the support of the initial measure equal to nu, and with the weights given by the density of the initial measure you want. So that is the interpretation of what the occupation measure is. And now you can try to solve the LP in exactly the same way. You'll just be fixing the initial measure to be not a Dirac but some other measure. This would be probably one line of code to change. And now you'll be getting bounds on the integral over the initial measure of these time average functions h along the trajectories of the OD sampled from with initial conditions sampled from this initial measure nu. So let's see what this will look like numerically. So here I picked the same system, Vantable oscillator, and I picked the initial measure to be uniform on this box. And these are just trajectories to give you some visualization what they look like. And I decided to compute the bounds on the same function as before. And now the true value is approximated using Monte Carlo, but to very high accuracy. And you can see that the computed bounds using SDP enclose it relatively well. But even for time equals to 1, you have to go relatively deep into the hierarchy. For time interval 10, you have to go even deeper, and even at order 7, you do not close the gap completely. So the takeaway here is that the longer the time interval and the more spread out the initial measure is, the deeper you'll have to go to the hierarchy, and this is what's brought out by the convergence analysis as well. And so now the next step in generalizing the approach is to take a free initial measure. And let's see what we can get out of this. So now, once you take the free initial measure, it's no longer true that the set P is a singleton, because you can put whatever initial measure, and so even if you restrict yourself to Diracs, you can produce many different trajectories starting from many different initial conditions. And therefore, in order to prevent unboundedness, you should at least normalize the mass of the initial measure to be 1 or any other number. And if you do that, and if you stay with the same function as before, then you can easily see that now what you will be getting is lower bounds on the infimum over all initial conditions belonging to the support of the initial measure. So this is now capital X0 of this time integral. So this is now no longer trivial. You would not be able to evaluate it so easily just using Monte Carlo. You could still sample in X0, but this would be more challenging, and this is probably already more challenging than static polynomial optimization, because now we are really optimizing something where the variable lives in Rn, but the process that produces the value is this ODE. So this is something more complex, and you can make it even more interesting by considering constraints. So the very strong point of this approach in the dynamical system is that constraints are handled very easily by simply including them in the supports of the respective measures. So you could decide that you would like to take the infimum only over those initial conditions such that the trajectories starting from them stay in a constraint set X and end up in some constraint set XT. Normally, this would be quite hard to do in other solution techniques, such as those based on Pontryagin principle and so on, where constraints are very, very messy to handle. But here, it's very, very straightforward, and again, basically a couple of lines of code to include the constraints in this problem. And so I'll not show you numerical experiments on this, but rather I'll talk about the problem of regional attraction, which is very much related to this kind of reasoning based on constraints. And it also has a free initial measure. So this is the problem statement. I'm looking for the set of all initial conditions to my ODE, such that these initial conditions are steered to a given target set xt without leaving a given state constraint set capital X. So that's the gray region. So in particular, I do not like trajectories which leave the state constraint set at any point, even though they end in xt. And I'll try to solve the problem using this hierarchy. The way I'll go about it is quite straightforward. Once you know the solution, it's easy to explain. We'll have a free initial measure, free occupation measure, free final measure, with the support of the final measure being in the target set and the support of the occupation measure being on the time axis and the required state constraint set, and we'll be maximizing the mass of the initial measure, subject to the constraint that the initial measure is dominated by the Lebesgue measure. And so this constraint, it's crucial to understand it. It's what you can prove is that this is equivalent to saying that the initial measure is absolutely continuous with respect to the Lebesgue measure supported on X, with density being less than or equal to 1 almost everywhere. And once you have this realization, it's quite easy to convince yourself that the solution to this LP will indeed give you what you want, and it's going to be the initial measure supported on the region of attraction restricted. So it's going to be the Lebesgue measure supported on the region of attraction. So the claim is that an initial measure with density equal to 1 on the region of attraction and 0 everywhere else is optimal. And the proof is basically by arguing all the possible cases that can happen. Basically, if you had something which is supported on the region of attraction, but it doesn't have density equal to 1 almost everywhere, then you can still add more mass, and there is nothing that prevents you from doing so. If you had something which overshoots the constraint 1 on the density, then this would not be feasible. On the other hand, if you had something which satisfies the constraint of density being less than equal to 1, but is not supported in the region of attraction, then you would necessarily violate the constraints on the supports of the occupation measure or the final measure, or you would violate the constraints on the dynamics, the linear constraint. So this cannot be feasible either, and therefore this is necessarily optimal. And the formal proof is not far from this argument. And so now, if you want to do something computationally, you would typically look in the dual LP, which is in the space of continuous functions. It has 2 dual multipliers, functions v, which is C1, and function w, which is continuous. And they satisfy certain sign constraints on given sets. I'll not analyze this in detail. I'll just tell you that if you do so, then you'll realize that any function w which satisfies all of these constraints will necessarily be greater than or equal to the indicator function of the region of attraction. So the w will look in this way, and therefore if you cut it at 1, so you take unit super level set, you get an outer approximation to the region of attraction. And then what you can prove further is that if you take a minimizing sequence, then you get a convergence in L1 under compactness assumptions. And this also implies that the convergence of the outer approximation to the region of attraction converges in the sense of volume discrepancy tending to 0. And here is a numerical example on the Vantable oscillator. This is the function WK, which you then cut at 1, and you get an outer approximations. And if you increase the degree, they converge. So the dark gray is the desired regional attraction. Light gray is the outer approximation. So this was very briefly how this moment sum squared hierarchy can be used for this problem. Now let's see if we can generalize it yet further by adding control input. So this once you start adding control input, normally things get much harder. In this moment sum of squares setting, in terms of implementing things, things are not much more difficult. The theoretical analysis becomes far more involved. So the proof that I showed you at the beginning would be much more involved, and it would not be true in the way that I stated it. But in terms of the conceptual way of manipulating the measures, everything is quite straightforward. Basically, we just add a control argument to the occupation measure. So now the measure will be supported on subsets of the time axis, state space, and the control space. And the definition will be exactly the same. I can't draw a third axis, so you would also be looking at which portions of the control space, the joint trajectory of x, and you intersect, and how much time it spends there. And the equation that you can derive that each triplet of this measure has to satisfy is exactly the same one. It just has the third argument in the occupation measure, and the vector field now is dependent on the control, on u. So this equation still holds, but what becomes much more delicate is the uniqueness of solutions to this equation, which is no longer true, because you can produce many different trajectories starting from a given initial measure, even if the initial measure is a Dirac. So this certainly does not have unique solution any longer. The natural question is, so what does the set of solution look like? Is it generated only by the trajectories of my ODE? And the answer is no. What you have to look at is trajectories of this convexified ODE. So this is now a differential inclusion where the velocity belongs to the convex hull of the vector field, where you take the convex hull over all the possible velocities that you can generate by your control input u. And then what you can prove is that indeed any tx marginal of a measure which is feasible in this, which belongs to this at p, is given by this superposition. So here you are integrating over trajectories which solve this convexified inclusion, and you are associating to them these occupation measures. And this is the statement. So I think it's quite neat that you can actually go back to the very beginning of the talk, and you can produce a measure which is supported on the solutions of this convexified inclusion. So this sort of measure does appear, but it comes up in a rather indirect way, and proving the statement is much less trivial than the first statement that I showed you at the beginning. And it has been proven at various levels of generality by a number of people. I'll not try to make an exhaustive history of this kind of results here. Currently, we are looking into whether one could arrive at an elementary statement or something which would be easy to teach and understand. So far, the proofs depend on far from trivial results of Ambrosio or other results from Winter. So the natural question to ask is, am I losing something by considering here this convexification on the right-hand side? And the answer is that it depends on what your problem is. But in most problems coming from engineering, you are not losing very much, because what you can prove is that the trajectories of the original ODE, so this is x dot equal to f of xu, are dense in the trajectories of this convexified ODE, which is a result due to Filipov and Vasevsky, and basically it's very intuitive, because you are in continuous time, and so you can change the vector field here on the right hand side as fast as possible, so that you can generate anything in the convex hull. So this is the intuition, and it's basically related to the Floquet type arguments. And so now, equipped with these results, you can directly tackle the regional attraction with control, where the problem setting is simply, I'm looking for all initial conditions that you can steer to a given target set using admissible control inputs. The formulation looks exactly the same as before, but now in the occupation measure, you are just constraining the support of the occupation measure to be to have a third component, and that third component should be in the set of admissible control inputs. And you can prove exactly the same convergence results of L1 and of the after approximation in terms of the volume discrepancy tending to 0. And so, a numerical example, which is this Brocket integrator, where we know the result semi-analytically, which is one of the few examples where this is actually the case. Otherwise, this problem is very hard. So the dark gray is the true regional attraction, and the light gray is the outer approximation. The problem is of steering the system to the origin, subject to constraints on the states and on the control inputs. And this is the outer approximation for degree 5. And so now this up until this point, this has been basically a review and some older results. And so now a little bit of new work in this direction, which pertains to adding data. So we'd like to bring measurements, real-time measurements to the picture. So this would be the setting. I have now, it'll be a semi, let's say, gray box setting, where you still know the vector field F, but you have an unknown parameter theta. And you have a prior information on the theta that it belongs to some set capital theta. And besides this prior information, you also have a measurement mapping H, which maps the state to some to Rn or to some Euclidean space. But this measurement is corrupted by noise, and this noise takes values in a compact basic sim algebraic set. And so beyond this prior information, you have a collection of data that you have measured on the system. So you have a timestamps, which tell you when you made the measurements. You have the value of the measurements, and you have also value of the control input that affected the transition in between the timestamps. And you assume that the value of the control input is constant in between the timestamps. And this is what it looks like. You have some unknown trajectory in behind, which you do not see, and the only thing you see are these y1, y2, y3, and y4, and they are corrupted by noise. They are the maps of the state at those time instances corrupted by noise. So this is what you are given, and the object you would like to determine is the data consistent region of attraction, which is the set of all initial conditions which you can steer to a given target set, for all theta which are consistent with the prior information and with the data. You can write it mathematically in this way, where the ROA of theta means a regional attraction with the value of theta given. And so we're intersecting over the prior information and over all consistent, over theta consistent with the data. So this is the problem setting, and let's see how we can solve it using this moment sum of squares hierarchy. And so the first step there will be the same as we have done before, basically with the only difference of augmenting the state space by theta. So this is a classical trick. You are just adding zero dynamics of theta. So now the state space will be x and theta. And then you would like to somehow link this to the data. So you would like to influence the supports of the initial measure, occupation measure, and final measure by the information that you have in the data. And so one way of doing it is to construct a chain of initial, occupation, and final measures, where the support of the initial / final measures will be at the timestamps where you had the measurements, and the final measure from the previous segment will be the initial measure of the subsequent segments. And the support of the final measure will be constrained by the measured data. So for example, for this mu02, we would know that y2 minus x at x at t2, so y2 minus x minus h of x should be in the noise set. So that's the set bold W that you've seen before. And so that would be the constraint on the support of mu02, and this is related to all the work on set estimation. And now you need to link this to the problem of regional attraction, and that's done through the marginals of the corresponding measures. So here we'll take the theta marginal of the initial measure of this chain, and we'll equate it to the theta marginal of the initial measure which comes into the regional attraction problem. You could think of other ways of linking it, and you could also work with theta marginals of the occupation measures and final measure, but as it turns out, this is enough to get convergence results. When you write this down, you end up with this kind of problem. Here in the first bit, this is what you have for the regional attraction problem, with the addition of the theta components in the support of the measures. So SPT here is the support of the respective measures. Here you have the data consistency constraints, where the support of these final / initial measures of the chain are constrained by the measured data and by the prior information. So these are basic semi-algebraic sets in the x and theta space, and this is the coupling, which is just the linear constraints on the two measures. So this is an infinite dimensional linear programming problem in the space of measures. And what you can prove about it is that the optimum mu0 is going to be equal to the regional attraction. It's going to be equal to the Lebesgue measure restricted to the set of x and theta, where x belongs to the regional attraction of a theta, and the theta ranges over all the consistent values of theta, which are consistent with the prior information and data. So this is not quite what you would like. This is not the data consistent regional attraction. You would like to here intersect over all the theta. So let's see how we could do that. The side remark, which we'll be using later, is that the theta marginal of this optimum mu0 is Lebesgue measure on the data consistent set of parameters theta. It's scaled. And so now looking at the dual, the interesting things will happen here. The dual will again have multipliers W and V, but it'll also have many other multipliers VI, which come from this chain of measures, and it'll also have coupling phi. So these are the standard constraints for the regional attraction, and they are coupled to the data consistency constraints through this dual multiplier phi, which is the multiplier of the coupling constraint, and the data enter here. And now what you can prove is that any feasible point W in this dual will give you an outer approximation to the data consistent regional attraction if you minimize over all of theta in the data consistent set. And you can also prove convergence if the interior of the noise set is non-zero, so that's a technical constraint. And then you can prove convergence from the outside of these outer approximations in terms of the volume discrepancy tending to 0. And this holds for any minimizing sequence, which could come from the SDP outer approximations, provided that all the sets are Archimedean or satisfy Archimedean conditions and their algebraic description. And so this is a little technical argument because you are handling this partial minimization there. So the last question that remains basically is how can we do this partial minimization, because we are minimizing over the data consistent set, which we do not know a priori. So this is not a semi-algebraic set. This is a set which we don't even know. More formally, we would like to find the value function zeta of this parametric optimization problem, where this D is this data consistent set. And one way of doing it is through gridding. So you could decide to verify for each data from the prior information through forward integration or solving of optimal control problem, whether it is in the data consistent set or not. This would be quite costly, but it's a valid way of doing it because you need an upper bound here. And the second approach, and I think it's a bit more elegant and more in line with the Poema workshop, is to use the second LAAS hierarchy or slight extension of it to construct a converging sequence of upper bounds on the value function of this parametric optimization problems. So as whoever knows the second LAAS hierarchy, that's the hierarchy of upper bounds on polynomial optimization problems. Now the problem is a parametric one, so we have this x which enters, and we would like to find a function which approximates the solution to this optimization problem from above for each x. So the idea will be to consider densities rho d, which are densities for each x. So for each x they integrate to 1. For each x they are non-negative. And we'll be pushing the integrals with respect to these densities of the objective function w down by some polynomial rho d. So this is the idea of that. And you can prove that if you replace the non-negativity constraint by inclusions into quadratic modules, you get convergence with the final caveat, which is the one of not knowing the moments of the Lebesgue measure over D, because that's the data consistent set which you don't know. But fortunately, we get them from the solution to the primal LP, or you get them in an approximate form from a solution to the primal SDP relaxation. So you can actually solve the numerical using those approximate moments, and if you do some little tricks, you can still maintain the convergence. So this was this little remark there, that you get the Lebesgue moments from the primal problem. So there is this nice link between the primal and dual solution. And so I'll finish with some numerical experiments. The first one is on an unstable linear system. So we have this linear system. The true value of theta, which was used to produce the data, is equal to 1. We have some prior information, which is that the theta belongs to -1 and 1. And then we have 4 noisy measurements along the trajectory of x2. So this is not very many data points, but even with those, you can make meaningful statements, and you can see here that as you increase the degree in the hierarchy, you get closer and closer to the true data consistent region of attraction, which is this dark region, which have been approximated using brute force gridding technique, which was quite costly. That's why it is jagged. And the second example is a nonlinear one, Vantable oscillator, where the true value of theta here is 0.2, and the prior information is quite spread out, so that you get some trajectories which escape to infinity. And now we'll look at what happens as you change the number of data points and the noise level. So here in this top left corner, you have very few data points, just 2, and relatively high noise level. So your estimate is very conservative. When you increase the number of data points, you get more confident, so you get more information about the parameter, and so your estimate becomes larger in the state space. The same happens when you decrease the noise level. Your estimate gets larger, and when you do both, then your estimate gets yet larger. So here you have more data points and lower level of noise. And so I'll finish just by mentioning what happens if you do not know any any model and you have only data. As it turns out, you can still do something meaningful even in this setting with very little information. I'll not go into any details, but it turns out that you can derive probabilistic bounds and even guaranteed bounds, provided that you know at least a Lipschitz constant of the transition mapping F. The downside is that this comparatively needs much more data than the model-based or gray box approach that I have just presented. So there is a trade-off. On the other hand, this approach is computationally much cheaper. You end up solving on an LP, so you can go to higher dimensions. And I'll leave you with the summary, where I'll say that I try to convince you that measure optimization can solve a lot of problems from dynamical systems. It appears that the harder the problem is, the more useful the approach is. So you would certainly not want to use this approach to solve an ODE with a given initial condition, but you would perhaps want to use it to solve an optimal control problem or a problem of regional attraction estimation. And as much as you can formulate this problem in this setting, the numerical side is always challenging because of the curse of dimensionality. These SDPs do grow quite quickly in terms of the dimension of the state space. And so it's very important to exploit structure. One of the possibilities is sparsity, which we have done recently with Corbin and Schlosser. And he already talked about it once at the BrainPop workshop, and I'm sure he will get to talk about this sometimes in the future. And this is all from me. Thank you.